Hi everybody, this is Math 025 for Hartford Community College. This is Module 3. And we're going to look at rational expressions in this module. A rational expression is the quotient of two polynomials. So kind of think of a quotient as a fraction. So that's what we're looking at here. A rational expression can be thought of as an algebraic fraction because we have those variables in there. And you can see on here examples A and B are two examples of rational expressions. And the first thing we're going to look at is how to find when an expression is undefined. Now, we know when we have a fraction, we can't have 0 in our denominator. So when we have a rational expression, that expression is undefined when it is evaluated at a value and the denominator is 0. So for example, for the first one, I have 7x plus 15 in my denominator. If I plug in like the number 2, which I know will not work, but if I were to plug in the number 2 and it gave me a 0 after I did all the math, that would be a value for which that expression would be undefined. And it's only the denominator that we have to worry about being 0. So what we're going to do is to figure out when our value would be, or our expression would be undefined, we're going to take a look at our denominator, and we're only going to worry about the denominator. So for A, I have 7x plus 15, and I'm going to set it to 0 and solve that equation because I want to figure out, well, what will make x equal 0? This is a linear equation, so I'll just start by, subtract 15 from both sides. So right now I have 7x is equal to negative 15, and then I'll divide by 7. So x equals negative 15 sevenths. And what this means is my denominator can be any value except x cannot be negative 15 sevenths, because when it is that, it will give me a 0 in my denominator. So I can plug in any number that I want for x except negative 15 sevenths. That will make the expression undefined. Now for B, again, the numerator right now, I'm not worried about it because that can be a 0, so that doesn't matter. It's only the denominator we're worried about when we're looking for undefined. So I'm going to take my denominator again, my 2a squared minus 6a, and set that equal to 0. Now this is a quadratic, so we have to factor like we did in the past couple modules. So I do see a greatest common factor here, and I can pull out a 2a from both of these. So when I factor it, I have 2a times a minus 3 equals 0. And then just like we did before with our zero factor theorem, we'll put 2a is equal to 0. And a minus 3 is equal to 0, and we'll solve. So here we'll divide by 2, which 0 divided by 2, or 0 divided by any number, is 0. And then the next one we'll add 3 to both sides, so I get a equals 3. So this expression is defined for any value for a except a cannot equal 0 or 3. When a equals 0 or 3, I get a 0 in my denominator, and that will not work. Okay, so any other value I can plug in for a, but for 0 and 3, it will give me a 0 in my denominator, which makes the expression undefined. All right, so here we have 2 more problems that we want to find where they are undefined, where the expression is undefined. So again, I'm only focusing on the denominator when I'm looking for where it's undefined. In my first one, we have y squared minus 15y plus 14. And again, we'll make that equal to 0. Now, this is something that I can factor, so I'm going to factor it. It is an easy trinomial. So for 14, I know to get 14, I can do 1 and 14 or 2 and 7, but I need a negative 15. So I'm going to have to use 1 and 14, and they're both going to be negative. And again, that will equal 0. So now, remember, I set those both to 0. And we will add 1 to both sides. So we get y equals 1. We'll add 14 to both sides. So y equals 14. And again, here, for any value for y, you can plug in any number except y can't equal, we'll write it in roster notation, 1 or 14. Because those values will make the expression undefined. So those are the only two that won't work, because when we plug them in, they will give us a 0 in our denominator. All right, let's look at D. And again, we're going to start off by making that equation 3t squared minus 8t minus 3 equal to 0. Now, this is a hard trinomial, so let's go ahead and box it. We'll put our 3t squared here, our 3 here, and then I know I need my t's and a number. So we'll multiply 3 times 3. It gives me 9. My factors of 9 are 1 and 9, and 3 and 3. I need it to add up to a negative 8, so I have to use the 1 and 9. It's going to make my 9 negative and my 1 positive, because negative 9 plus positive 1 will give me negative 8. So I'll fill those into my box. And now I'm going to factor across on the bottom first. So the greatest common factor for 1t and 3 would be 1. For 3t squared and 9t, my GCF would be 3t. Now when we factor up, for 3t squared and 1t, my GCF would be t. For 9t and 3, my greatest common factor would be 3. So when this expression is factored, it factors to 3t plus 1 times t minus 3. We'll set that equal to 0 again. And then, again, solve each equation set to 0. So for the first one, 3t plus 1 equals 0. I'll subtract 1 from both sides. 3t equals 0, divide by 3. So t, oops, no, it doesn't equal 0. Let me fix that. So hold on. It would be when we subtract 1, we get 3t is equal to negative 1. Divide by 3. So t is equal to negative 1/3. And then for the other equation, we'll add 3 to both sides. So we get t is equal to 3. So here, my expression is defined for all values of t except t cannot equal negative 1/3 or 3. All right, we're going to look at our last two, where we're going to find out where the expression is undefined. For E, if I look at that one, I have two terms and I have subtraction. And if I look at those two terms, they are both perfect squares. So I can factor that as our difference of perfect squares. So remember, it will factor to 3r minus 5 times 3r plus 5. And we're going to make it equal to 0 because that's what we're solving. So then I'll set each equation to 0. So 3r minus 5 equals 0. And 3r plus 5 equals 0. We will add 5 to both sides for the first one. So we get 3r equals 5. Divide by 3. So r equals 5/3. And then for the second one, I will subtract 5 from both sides. We get 3r equals negative 5. Divide by 3. And r is going to equal negative 5/3. So again, this expression is defined for all values of r except the values that make the denominator 0. So that means that r cannot be 5/3 or negative 5/3. because those two values will make the denominator 0. Now for f, again, we're only concerned with the denominator. And my denominator here is nice because it is only 13. There's no variable in there. So there's nothing there. 13 is a constant term. There's no variable there to change the 13. So for this one, it doesn't matter what I plug in for z on the top because I can get any number on the top. So for this one, because there's no variable down at the bottom, it's just a number, my domain here will be all real numbers. That means there's nothing that makes this expression undefined because, again, there's no variable in the bottom to turn that 13 into a 0. Okay, so now here we are doing the same thing basically that we were doing before. We're finding the domain of each rational function. And remember, domain is what you can plug in for the variable to give you a true or, I guess what you call kind of like a legal expression in math. What we just did, we found out where the expressions were undefined. That was helping us find our domain. And you probably heard me mention, oh, the domain of this one is all real numbers except these two numbers. So now what we're going to do is we're going to focus on finding our domain, and then we're going to write our answer in set builder and interval notation so we can see what the domain is and write it the way we would in math to kind of describe the domain. So for A, again, we're concerned with that denominator to find the domain. I have x minus 12, so I'm going to find out where my domain is undefined. So x minus 12 equals 0. So we're going to add 12 to both sides. So this means that every number can be plugged into our equation except for 12. So when I write this in interval, let's do set builder notation first. So set builder, remember, you start off with the braces, and you have the set of all x such that x is the element of real numbers, because we can use any number except x cannot equal 12. And if you recall with your set builder notation, we always start off with the set of all x such that x is an element of, and in our case, we're always talking about real numbers for these problems, so we're going to put our real numbers there. And then what you're going to have to change is where it's undefined, so you have to list that. Now, when we do interval notation, basically, interval notation is copying that number line. So if I were to graph this on a number line, I can use any number except 12. I can't use 12. So that would be almost like having an open circle, if you recall, for graphing, on 12, and then shading to the right and to the left, because it's anything but 12. So now if I'm going to put this in interval notation, remember interval notation, we use parentheses and brackets. Parentheses would be if it is greater than or less than, or if it's on a number line, use that open circle. A closed circle, or greater than or equal to, less than or equal to, those are brackets. So here, because it goes on infinitely to the left, that is going to be negative infinity, and it's going to go up to 12. And because it doesn't include 12, I'm going to put parentheses around it. Now, the other part of the graph, it goes from 12, starting right after it, not including it, all the way up to positive infinity, because we have that arrow shaded there. Now, to connect these two to show that they are connected to each other, you're going to put a U between them, because that shows that this is the entire interval notation. And really what it's saying is it goes from negative infinity to 12, but doesn't include 12. And then after 12, it goes to positive infinity. So, in previous classes, you've seen set builder and interval notation. Hopefully, it will come back to you a little bit. it is something, you might want to review a little. And again, you can always, if you need some extra help, talk to me and we can set up and have you look at some, we can meet for office hours, or I can get you some other videos where we talk about set builder and interval notation to help you out. Next for B, we have 13t. So we're going to take our 13t and again set it equal to 0, divide by 13. And we know that here t, it can't equal a 0. That's where the expression is undefined. So again, for set builder notation, it's going to look much like it did over here. The only thing that's going to change, so we have the set of all x such that x is an element of real numbers. And then the only thing we'll change is x, instead of not equaling 12, it can't equal a 0 here. And then also your interval notation will be similar, except now we have that 0 that's not included. So we'll start at negative infinity, go all the way up to 0, but don't include it. Put our U for union, and then start right after 0, but don't include it, all the way to positive infinity. And that will be our set builder notation here and our interval notation for that expression. Okay, so now when we look at C, this is another one like the last one we did when we were finding where they were undefined. For C, I only have 15 in my denominator. So remember, we don't have a variable there to modify that or make it into a 0. So that means that my domain here is going to be all real numbers. I can plug anything I want in for C at the top, and it will make the expression a defined legal expression. So when we write this in set builder notation, all right, we have the set of all x such that x is an element of real numbers. And we don't have to worry about putting in x can't equal anything. We can just say the set of all x such that x is an element of real numbers. And then because every single number is included, when we do it in interval notation, it would just be negative infinity to positive infinity. So that would be our interval notation for that one. So that one's kind of nice and easy. I like it. For D, we do need to take our expression, our 4y cubed minus 49y, and set it equal to 0. I do see here that I can factor out a y. So it'll be y times 4y squared minus 49 equals 0. And then I do notice the 4y squared minus 49, two terms here, I do have subtraction, and they're both perfect squares. The square root of 4y squared is 2y, and the square root of 49 is 7. So I'm going to go ahead and factor that in my difference of perfect squares. So it'll be y times 2y minus 7 times 2y plus 7 equals 0. And then when we set them all to 0 and solve, we get y equals 0. We have 2y minus 7 equals 0 and 2y plus 7 equals 0. So for the first one, I'll add 7 to both sides. We get 2y equals 7. Divide by 2, so y equals 7 halves. And then for this third one, we'll subtract 7 from both sides. So we have 2y equals negative 7. Divide by 2, so y equals negative 7 halves. Now, for this one, it is going to be kind of a pain to put into interval notation, but we can do it. So we'll start off with set builder because it's nice and, well, kind of easy. And I'm going to write it over here on the left, but, we'd have our braces and the set of all x such that x is an element of real numbers. But we know x cannot equal 0, because we get that from up there. Negative 7 halves or 7/2. Okay, so now when we do our interval notation, basically anything but 0, -7/2, and 7/2 is included. So we have to kind of think, put these in order. So I'm going to do a little erasing so we have a little bit more room here. All right, so if I were to put these in order and put them on like a number line, all right, and I'm not going to evenly space it out, but here's -7/2, here's 0, and there's 7/2. Everything but these three numbers are included. So all this stuff to the left, in between these two, in between these two, and then everything to the right. So when I do my interval notation, I'm going to start at the left and work my way to the right. On the left, because the arrow is shaded, -∞, and then it goes all the way up to -7/2, but it doesn't include it. So that means we put parentheses around it. I'm going to need a union there. Next, it's between -7/2 and 0. So we're looking at this part right here. And then I need another union. And then we got to put in the other between 0 and 7/2. So we're going to have 0 to 7/2. And then our last part with our union is going to be 7/2 to +infinity. So that's a +infinity there. Okay, so excuse me, kind of long here, but this would be your interval notation for that one. And again, look at that number line, find out where your stopping and starting points are, and that's really where your numbers aren't included, and then fill in everything in between those spots. All right, so here we're going to look at one more where we're going to find the domain and write it in set builder notation and interval notation. So here again, we have a quadratic, so we have a squared minus 5a plus 6, and we'll set that equal to 0. We're going to go ahead and factor it. So it's an easy trinomial. And I'll have a and a. It's a minus and a plus, so it'll be two negatives. To get 6, I can do 1 and 5, or no, excuse me, 1 and 6, or 2 and 3. But I need a -5, and my signs are going to be the same. So I'm going to use -2 and -3 equals 0. Then I'll set each expression to 0. And so for the first one, we will add 2 to both sides. So we get a equals 2. Here we'll add 3 to both sides. A equals 3. So again, my domain can be any real numbers except a cannot equal 2 or 3. So when we do that in set builder notation, we'll have the set of all x such that x is an element of real numbers, but x cannot equal, and I used x, it should be a. Let me go back and erase for you guys and fix that. All right. I'm going to keep it in the same variable. So the set of all a such that a is an element of real numbers and a cannot equal 2 and 3. All right, so you do want to keep the same variable. I tend to go with that x because that's what I'm used to. I think I might have made that mistake on the past slide. I think I did x instead of y. So again, just put it back, go back and fix that, put it in your real variable that you're using, like a or y or x. Now we do want to do interval notation here as well. We can include 2 and 3. So again, if I were to look at this on a number line, 2 and 3 are the numbers that aren't included. So think of those as our open circles. But everything else is included. So again, start at the left and work your way to the right. The left arrow is shaded, so that is negative infinity. And it goes all the way up to my 2, but doesn't include it, so we'll put comma 2. Put our union. The next shaded part is between 2 and 3, but again, it doesn't include it, so we're going to use parentheses. Put our union there. And then the last part is 3 to positive infinity. And that would be my interval notation for that problem. All right, the next thing we're going to do is we're going to simplify rational expressions. And this is kind of like simplifying fractions. To simplify a rational expression, you have to factor your numerator and denominator completely, and then cancel out any common factors. And just a reminder here, factors are what you multiply together. So when we're doing that, we can't multiply part of one expression and not part of the other. We have to factor out entire expressions. So let's take a look for A. If I go to factor A, for the top, I know I can pull out a 2. So I'm going to have 2 times x minus 3. And then on the bottom, my GCF would be a 4. And that will give me x minus 3. Now, when you're looking here, the top has 2 factors. It's 2, which is a factor, times x minus 3. And this whole expression is a factor. Here we have 4 times x minus 3, 2 factors down here. And if you notice, the x minus 3 on the top and the bottom is exactly the same. So remember, when you have a fraction and you have the same thing on the top and the bottom, it equals a 1. So that factors out. That can be simplified out. That leaves us with 2 over 4, but we do know that we can simplify that 2 over 4 to 1/2, just simplifying a regular fraction. So it went from this scary problem down to just 1/2 when we simplified it. All right, let's take a look at B. It looks like the top x minus 2 is already factored. I really can't do anything with it. Now, if it's an expression and it helps, start putting parentheses around it, so that way you don't simplify just part of it. On the bottom, let's see here. I can pull out a 2, so it's going to give me 2 times x squared minus 4. And then I do notice that this is the sum, or not the sum, but the difference of perfect squares. So I can factor that again. So I have x minus 2 over 2 times x minus 2, x plus 2. My pen went off. There we go. X plus 2. All right, now looking for common factors. I have x minus 2 on the top and the bottom, so that is a common factor. I can cancel that out. Now, remember, when you have the same thing on the top and the bottom, it equals a 1. If there are other factors there, you don't need to put the 1 in. But on the top, because that was my only factor, I do need to write that 1 in. So when I write my final answer here, I'm going to have 1 over 2 times x plus 2. Because you can't just get rid of your numerator. We need that numerator there. So this would be my final answer. And you want to leave it in factored form. You don't want to distribute that 2. So this would be your final answer for that one. All right, let's take a look at C and factor that one. I do see for the numerator that I can pull out a 2 for a greatest common factor. So it will be 2 times x squared minus 3x plus 4. And then on the bottom, I can pull out a 10, and that will give me x squared minus 1, which on the bottom, that x squared minus 1, I see right away, difference of perfect squares, so it'll factor to x plus 1, x minus 1. All right, now on the top, I pulled out a 2. This x squared minus 3x plus 4. It looks like it should be factorable. Let's try it. So my C value is 4. My factors of 4 are 1 and 4, 2 and 2. But I need a negative. I have a negative and a positive in that order. So I need 2 negative signs. If I make these both negative, they're not going to give me a negative 3. And these as well. So that means that this expression, the x squared minus 3x plus 4 is prime. We can't factor it. So it's factored as much as we can. Now, when we look at our expressions, there's not a lot that we can take out. Because remember, this x squared minus 3x plus 4, that's one factor. So if we want to cancel it out, we have to have the whole thing on the bottom. And I don't have that. This x plus 1, it's one whole expression. So I can't just get rid of my x's here. There's nothing I can cancel out. The only thing that I can do is this 2/10. They're factors, and I can simplify that as like a regular fraction, so I can turn it into 1/5. And again, because I have already something on the top, I don't need to put the 1 at the top. I'm just going to keep my x squared minus 3x plus 4 over x plus 1, and we keep our 5 down there. So 5 times x plus 1 and x minus 1. And for that one, unfortunately, that's all we can do. We can't do any more simplifying. Let's take a look at D. So for D, I do see there is no greatest common factor that I can pull out on the top or the bottom. So I'm going to go ahead and box the top. So I have 4x squared, and I have 1. 1 times 4 is 4. I need a negative 4 here. So I'm going to do negative 2 and negative 2, because that will give me 4 when I multiply and when I add. We're going to factor across. So 2x and 1, the greatest common factor is a 1. For 4x squared and 2x, my GCF will be 2x. When we factor up, we have 4x squared and 2x, so that greatest common factor is going to be another 2x. And then 2x and 1, it's going to be a 1. So that top factors to 2x minus 1 times 2x minus 1, or we can make it 2x minus 1 squared. The bottom, let's factor that. So we're going to have 2x squared and a 5. 2 times 5 is 10, so we can use 1 and 10 or 2 and 5, but I need a 9. And I have a plus and a minus in that order, so I need 1 positive, 1 negative. That means I'm going to use the 10 and the 1. So I'll have a positive 10x, which I'll put in that box right there, and a negative 1x. So when I factor across, the greatest common factor for 1x and 5 will be 1. The GCF for 2x squared and 10x will be 2x. When I factor up, my GCF for 2x squared and 1x will just be x. And 10x and 5 will be 5. So that would factor as 2x minus 1 over x plus 5. So again here, the top and the bottom, we have 2 factors. Factors are what you multiply together. So the expression 2x minus 1 is a factor. And I have 2x minus 1 both on the top and the bottom. So because they're exactly the same, we can cross those out. 1 on the top and then 1 on the bottom. The other 2 expressions, 2x minus 1 over x plus 5, are different expressions, so we can't cancel out, like I can't get rid of the x's because they're part of that expression. So I always say it's part of a family. Don't bust up your families. If you bust up the families, then I always say you're separating like a mom from the baby, and that would be not a good thing. So it's a family, keep it together. So this would be our final answer for that one. Okay, now we're going to look at E. And for E, on the top, we have 4 factors. So if you recall, this one, there's no GCF for all of the factors, but I can factor it by grouping. So on the top, we're going to start off with the first 2 factors. I can factor out an x. So I'll have x times y minus 6. Plus, I can factor out a 2 out of the second one, so it'll become 2 times y minus 6. And then if I factor that again, remember our greatest common factor here is now y minus 6. So it becomes, when it's factored, x plus 2, because we'll cancel out our y minus 6's, times that y minus 6, because you can't just throw it away. All right, excuse me, on the bottom, looks like I have a greatest common factor of y, so I'll pull out my y, and that will give me y minus 6 times y on the bottom. Now they're both completely factored, so we're going to see what we can cancel. And I do notice that I have 2 expressions that are exactly the same, y minus 6 and y minus 6. So that will factor out, and that leaves me with my final answer of x plus 2 over y. And we can't do anything else with that, so that would be our final answer. Now, for F, when you look at it initially, you're like, oh, these are already factored. There's nothing we can do here. And you're almost right. But notice I have x minus 4 and then 4 minus x, and they're kind of like opposites of each other. If I take this bottom expression, because I notice that they're opposites, I can factor out a negative 1. And when I do that, if I pull out a negative 1, and I want to put it on the side there, but if I pull out a negative 1, that's going to give me, I'm going to keep my x minus 4 on the top. And then on the bottom, I'm going to have negative 1 times negative 4 plus x. Which, if you look at this problem, now I have x minus 4, negative 4 plus x. They're the same thing. So I could really rewrite it like this, x minus 4 over x plus negative 4 or minus 4, and then times that negative 1. Because these are exactly the same, they cancel out. So it's going to equal, simplified, a negative 1. And this one, it's just think, if they're opposites of each other like that, and they're both subtraction, then that's always going to equal a negative 1. You can pull out a negative 1 out of that one. Okay, so let's see here. For G, again, I have 3p plus 7 times negative 7 minus 3p. And again, they kind of look like opposites. Now, I do know the top is all factored, so I'm going to keep 3p plus 7. On the bottom, let's pull out a negative 1 because I have negative 7 and negative 3p. So if I factor out a negative 1, it's going to give me positive 7 plus positive 3p. And again, 3p plus 7, 7 plus 3p, they are exactly the same. It doesn't matter that the order is switched on the bottom. These would cancel out, and again, it would equal a negative 1. All right, let's look at our last one here. So we have t minus 1, or excuse me, t minus 5 over 25 minus t squared. So the t minus 5 is factored. I know the bottom I can factor to difference of perfect squares. So 5 minus t times 5 plus t. Okay, and again, the 5 plus t, there's nothing I can do with that. But my t minus 5 and my 5 minus t, remember just from the last slide, these are opposites of each other. So they factor and they equal 1, but not a regular 1. They equal that negative 1. And then we're going to keep our 5 plus t because we can't do anything with it. So that one will give us a negative 1 over 5 plus t. All right, so the last thing we're going to do in this section for part 1 is looking at multiplying and dividing rational expressions. When you multiply or divide rational expressions, it's going to be very similar to simplifying rational expressions. The main thing you need to do is if it is, now you have 2 rational expressions, so you have to make sure both are factored completely. And then remember, if you have division, we don't actually divide fractions. We always do what I call the keep, change, and flip because we multiply by the reciprocal. So we keep the first fraction as it is, but in factored form. Change division to multiplication, and then you take the reciprocal or flip that second fraction. So we'll take a look at B in a second. Now for A, this one is a little bit hard because it's just 2 monomials to multiply across the top. So you can do it one of 2 ways. You can simplify before you multiply by looking at variables and numbers, or you can just multiply straight across and then simplify, which I sometimes honestly think is a little bit easier. So like I'm going to do 10 times 63, which will give me 630. X to the 6th times x will give me x to the 7th. On the bottom, 9 times 14 is going to give me 126. And x to the 4th times x to the 9th will give me x to the 13th. Now I can do simplifying here. I can go ahead and the 630 over 126, it actually goes in evenly 5 whole times, and I just divided it to C. So that's going to give me, like if I divide this, everything by 126, it's going to give me a whole number 5. And then when I deal, or think of it like this, as 5 over 1, with my fraction powers here, remember you subtract exponents. So if I do 7 minus 13, it's going to give me x to the negative 6th power. But remember, we want it to be positive. So that means that that x to the negative 6th is really going to be on the bottom, x to the 6th power. So it's going to give me 5 over x to the 6th power. Because remember, here when we subtract exponents, it always brings it up to the top. But if you have a negative answer, you have to bring it down to the bottom to make it positive. For B, we do have to do our keep, change, flip. So I'm just going to make it 12a cubed over 16b to the 8th times, instead of divided by, 20b over 9a to the 6th. So again, we flipped the second fraction. I'm going to multiply straight across, and then we'll worry about simplifying. So 12 times 20 is 240. And we'll have a cubed b. On the bottom, 16 times 9 is 144. And it will be a to the 6th. I'm going to keep a and b in the same order. And b to the 8th. Okay, now we do need to simplify that. I know that I can pull a 4 out of both 144 and 240. It's probably not the biggest number, but let's start there. So I divided a 4 out of both of those. It gives me 60 over 36. And I have a cubed b and a to the 6th, b to the 8th. Now, 60 and 36, I know I can pull out a 12 out of both of those. So when I pull a 12 out, 60 divided by 12 is going to give me 5. 36 divided by 12 is going to give me a 3. Now we have to deal with our A's. If I just subtract 3 minus 6, it gives me a to the negative third power. And 1 minus 8 will give me b to the negative seventh power. But again, I want those to be positive, so I'll rewrite my answer. I'll keep my 5/3, but the a will bring it down and the b will bring it down. So it becomes 3 a to the third on the bottom, b to the seventh on that bottom to make them into positive values. Okay, so C and D are both multiplication. So here we have to make sure everything is factored. So we're going to start off by factoring both rational expressions in C. For the first one, if we have x squared minus 4x plus 4, that will factor to x, I think minus 2 times x minus 2, because to get 4, you do 2 times 2, and that has to give me a negative 4. On the bottom, I can pull out a 2, so I have 2 times x minus 1. And then times, the 40 is in lowest terms, but x squared minus 1, we know can factor to x minus 1, x plus 1. All right, so really when we look at this, there's not a lot that we can do simplification-wise. When I rewrite this, I'm going to start off, I'm going to put the 40 first. I'm going to do 40. X minus 2 times x minus 2. Remember, we can simplify that to x minus 2 squared. Over 2, I have x minus 1 times x minus 1. So x minus 1 squared times x plus 1. And again, you want to keep it in factored form. I can't get rid of any expressions because they're not the same on the top and the bottom. It has to be one from the top, one from the bottom. But the 40 over 2 I can simplify. I know 2 goes into 40 twice, so it becomes 20 times x minus 2 squared over, that would equal 1, so we don't need it, x minus 1 squared times x plus 1. And that is about it. That's all we can do with that one. We can't really change it too much. All right, now for D, we have 9p plus 18 over 3p squared minus 3p. So let's start by factoring that. For 9p plus 18, I know I can pull out a 9, so it becomes p plus 2. And then on the bottom, I think we just pull out a p. So we have p times 4p minus 3 times, all right, now we need to factor 4p squared minus 11p plus 6. So I'm going to make a box down here. 4p squared and 6. We'll keep our p in there. 6 times 4, is 24. And we can do, again, 1 and 24, 2 and 12, 3 and 8, or 4 and 6. And I need 11. So I'm going to have to use the 3 and the 8. And they're both going to be negative. And that will give me a negative 11. So put the 3 there on the top and the 8 here on the side. It doesn't matter, again, where you put it. So when I factor, my greatest common factor for 8p and 6 will be 2. For 4p squared and 3p, we're going to have a p. And then 4p squared and 8p will be 4p. And 3p and 6 will be a 3. So that top is going to factor as 4p minus 3 times p minus 2. And then on the bottom here, we have p squared minus 4. Difference of perfect squares there, so it's going to factor as p plus 2, p minus 2. Okay. And now really what we need to do is to simplify this, we got to look for common factors that we can simplify or divide out. So the same thing on the top and the bottom. Right here I see p plus 2 on the top, and I have one on the bottom. So those can be canceled out. So I got rid of those. I also see I have 4p minus 3 on the bottom, and I also have that on the top. So they can cancel. And then we also have p minus 2 on the top and the bottom, so they can cancel out, equal 1. So the only thing that I have left for this problem is going to be 9 over p. Which is crazy to think that we started with this really scary problem, and this is all we ended up with, 9 over p. All right, so our next two are division. So before we worry about factoring or anything, we do want to do our keep, change, flip. So for the first one, I'm going to keep my first fraction as it is. It'll be x squared plus 7x plus 10 over x squared minus 4. And then division will change to multiplication, and we'll flip that second fraction. So it becomes x minus 2 on the top, x squared plus 6x plus 5 on the bottom. And now what we're going to do is we have to factor everything. So for the top part there, x squared plus 7x plus 10. I know it'll factor, let's see, x plus and x plus, because we have two plus signs there. And to get 10, we can do 1 and 10 or 2 and 5, and I need a 7, so we're going to use our 2 and our 5. On the bottom, x squared minus 4, difference of perfect squares, x minus 2, x plus 2, times, we have x minus 2 on the top there, it's already factored, and then on the bottom, x squared plus 6x plus 5. We'll factor 2. To get 5, we need 1 and 5, and that will add to 6, so it's going to be x plus 1, x plus 5. All right, so now we need to find common factors that we can divide out. On the top, I do notice right away x plus 2 and x plus 2. I can get rid of those. X plus 5 and x plus 5. Also, x minus 2. All right. Now, on the top, notice we've eliminated everything. But remember, when we eliminate, it equals a 1. So we can't just leave that numerator naked. We have to keep the answer there. So we're going to end up with 1 over x plus 1. And that would be our final answer. There's nothing else we can do. Okay, and the last one we're going to do for this video is f. Again, it's division, so we have to change it to multiplication. So we're going to rewrite it as 8q squared minus 18 over 2q squared minus 5q plus 3 times, and then flip that second fraction. So q squared minus 9q plus 8 over 6q squared plus 7q minus 3. All right, now we got to factor everything. For the top of this first fraction, I know I can pull out like a 2. And that becomes q squared minus 9. Which then I do recognize that q squared minus 9 is your difference of perfect squares. So I can go ahead and factor that again. Oh, and you know what? I made a mistake there. Let me fix that. when I pull out a 2, it's going to be 2 times 4q squared minus 9, which is still the perfect squares. So I can factor it again. And then 4q squared minus 9 is going to factor 2. I'm going to erase it so we can factor it again. 2q plus 3 and 2q minus 3. On the bottom, we have 2q squared minus 5q plus 3. It's going to be a hard trinomial, so let's box it. I don't see a GCF, so 2q squared 3. We'll have q with a number and q with a number. 2 times 3 is 6. We need a -5. And we're going to do 2 negatives because it's a negative and a positive. So it's going to be -3 and -2. So when I factor across for 2q and 3, my GCF is 1. 2q squared and 3q is going to be q. Factoring up, 2q squared and 2q will be 2q. And 3q and 3 will give me a 3. So that bottom is going to factor as 2q plus 3 times q minus 1. All right, and then q squared minus 9q plus 8. That is going to factor to, again, minus and a plus in that order is going to make it 2 negatives. So we're going to do q minus 8 times q minus 1 to get that -9 in the middle. And then our other one is hard trinomial. We're going to box it. We have 6q squared, -3 or 3 down at the bottom. And we need to figure out our numbers. So something that will multiply 6 times 3 to give me 18 that will add to +7. And I have a plus and a minus in that order. So I need 2 different signs. So we have 1 and 18, 2 and 9, or 3 and 6. And I can see I'm going to need to go with that 2 and 9 because I need a +7. So 9 is going to be positive. 2 will be negative. Factor across on the bottom. 2q and 3 is going to give me a GCF of 1. 6q squared and 9q will give me a GCF of 3q. 6q squared and 2q going up to the top will be 2q. And 9q and 3 will give me a GCF of 3. So now we have 2q plus 3 and 3q minus 1. All right, so now we can look for common factors we can factor out. I see right away 2q plus 3. I have 1 here and 1 here, so I can get rid of those. I have a q minus 1 and a q minus 1 that I can get rid of. And then, let me see here. Oh, you know what? This one down here on the bottom. Let's fix this. This was a minus sign. I had the minus sign up there. I didn't put it down there. So this one, those will cancel out, and the 2q plus 3 will cancel out over here. So we can get rid of all of those. Double check those signs, guys. See, I made a mistake. But here, we're left with 2 times q minus 8 over 3q minus 1. And that's all we can do. We can't do any more. It's all that's left.